Welcome back. So we're discussing some properties of Fourier transform, and we'll be discussing another property, that is the property of differentiation. It is an operation we do in time domain, and we'll see that what will differentiation transform into the frequency domain when we use Fourier transform. So again, if we have x of t, it can be expressed as this. That is, we are basically getting x of t from x of omega. That is the inverse Fourier transform using this equation, right? So in this notation, what it specifies is, this thing, which the factor that modulates the e raised power j omega t, it is basically the transform. This is basically the transform of x of t, this factor x of omega, which appears in this integral in the inverse Fourier transform. This is actually the transform of x of t. Now what we'll do is we will differentiate this expression on both sides with respect to time. So we have d by dt of x of t is equivalent to d by dt of 1 upon 2 pi minus infinity to plus infinity x of omega e raised power j omega t d omega. But the derivative is with respect to time, that's t. So we'll take all the other terms out. So 1 by 2 pi integral from minus infinity to plus infinity x of omega d of omega, it will be outside, and we'll take the derivative for the factor which involves the time t, which is this e raised power j omega t. Just a second. So this means it will be 1 by 2 pi minus infinity to infinity x omega d omega, and the derivative of this thing is e raised power j omega t multiplied by the derivative of this, the power, which will be j omega. So it will be 1 by 2 pi integral minus infinity to plus infinity j omega x omega, then e raised power j omega t d omega. Now if we compare this equation and this equation, it turns out the factor that modulates e raised power j omega t is this thing. Fine, just like in the first case, the normal case. This is the factor that modulates e raised power j omega t, and it is actually the transform of x of t. So by that logic, this is actually the transform of Fourier transform of d by dt x of t. Right? So we can say that if x of t has a Fourier transform of x of omega, then the derivative of this function, a derivative of this signal, will have a Fourier transform of j omega x omega. Again, you can see that the derivative operator is replaced by simple multiplication by j omega in the frequency domain. Right? Now you see differentiation का जो inverse operation, that is integration. So we can just extend this, and I think this will be a kind of assignment for you. Just try it at home, that if x of t is related with Fourier transform to x of omega, then if I perform the integration up to the time t of this signal x of t with respect to this, then the result will be that x of omega will be divided by j omega, right? Because differentiation and integration, they're kind of inverse operations. So if differentiation translates to multiplication in frequency domain by the factor j omega, integration will transform uh, to division by j omega in the frequency domain. Fine. Plus it will have some, because integration is always accompanied by integration constant, so it will always have some average or dc term. Fine. So try to prove this relation. It will be a similar kind of a thing, similar analysis. Just try to prove at your own places. Fine. So this is yet another property of Fourier transform. Then there's a property of conjugation. Conjugation and the conjugate symmetry. You are aware with complex conjugates. Fine. So it is something like this. If we have x of t is equivalent to a of t plus j times b of t, then we define its complex conjugate like this: a of t with the negative imaginary part. Right? And if x of t is real, it doesn't have an imaginary part, then we can conclude that x of t is the same as its conjugate. Fine. Now we'll try to understand this conjugation property in Fourier transform. So again, if we start with this, that x of omega is equivalent to minus infinity to plus infinity x of t e raised power minus j omega t d of t. This is the Fourier transform, the forward equation. And if we take conjugate on both sides, so on the left hand side I will have x conjugate omega, and on the right hand side I will have minus infinity to plus infinity x of t e raised power minus j omega t dt ka whole conjugate. Now on the right hand side there are two terms just wherein we have to apply the conjugate. One term is x of t, so x of t ka conjugate we will denote that by x conjugate t. Then there is e raised power minus j omega t. Now on the conjugates, the imaginary part is, the sign is reversed, so it will be minus j omega t. We will reverse the sign, so it will be simply j omega t dt. Fine. And then here, so I have x conjugate omega is equal to minus infinity to plus infinity x conjugate t e raised power j omega t dt. Right? Then if we do a simple substitution, if we put omega to be equivalent to minus omega, we will have x conjugate minus omega is equivalent to minus infinity to infinity x conjugate t e raised power minus j omega t dt, which means इसका जो Fourier transform है, it is x conjugate minus omega, because rest of the integral is the same as the standard form. Right? Comparing this and this, we conclude this. Okay? So conjugation state is that if I have a signal x of t whose Fourier transform is equivalent to x of omega, then इसका जो conjugate होगा x conjugate t, it will have a Fourier transform of x conjugate minus omega. Right? Now if xt is real, means it has no imaginary part, then in that case the signal and its conjugate, they are the same. So for such case we will have x conjugate minus omega is equivalent to x of omega. Fine. So this is for the real signal. Now associated with this conjugation is an important relation, what we call Parsevals relation. It's often used in communication systems. We will study the physical significance of this relationship in your communication course. It has to do with the energy content of the signal. If you go back to your chapter 1, we had studied power signals and energy signals in time domain, that is. There on we had the expression for the total energy of the signal and the average power of the signal. So Parsevals relation, it kind of relates the energy computation in time domain to the energy computation in the frequency domain. Right? Like I said, you will study the physical significance in the communication course. Here we will try to establish a relationship. In fact, we will start with the relationship and then we'll try to prove it. So as per Parsevals relation, if we have x of t and x of omega, they form a Fourier transform pair. Then the energy, total energy in time domain, which we calculated like this, square d of t is equivalent to 1 by 2 pi minus infinity to plus infinity x omega square d omega. And this is the relation. Now the term on the left hand side, it is basically total energy in the signal x of t as calculated in the time domain. Right? And Parsevals relation, it states that this total energy, it may be determined either by computing the energy per unit like this x squared t dt and integrating over all time, or by computing the energy per unit frequency, although 2 pi is outside, so it would be better just to make the statement like this. Fine. And integrating over frequencies. So this term here, x of t whole square, it basically is the energy per unit time. Right? So we find energy per unit time and then integrate over all the time. Alternately, we can find the energy per unit frequency. So this relation here is energy per unit frequency, and then integrate over all the frequencies to get the total energy content. And the two are equivalent. Fine. The two are equivalent. Because this has to do with the energy, so sometimes, again, this is something you may study in communication. This factor x omega square means the Fourier transform of x of t whose magnitude has been squared. It's often referred to as the energy density spectrum of the signal. Fine, because it tells you what is the energy content in the individual spectral components, individual frequencies. You learn about the physical significance of this relation in the communication course. Here we will try to establish this relationship. That is the total energy content in time domain and the total energy content in the frequency domain. So I'll start with this minus infinity to plus infinity. The left hand side, it is the square of the magnitude integrated over all the time with respect to time. So you can always express this as ये जो signal है x of t multiplied by its conjugate. Fine, because if a signal is multiplied by its conjugate, it just gives you the square of the magnitude. Fine. Then it is minus infinity to infinity. X of t will keep as it is, and we will write an expression for this in terms of Fourier transform, that is. So if x of t is equivalent to the relation is 1 by 2 pi minus infinity to plus infinity x of omega e raised power j omega t d omega, and if I take conjugate on both sides, it will be 1 upon 2 pi minus infinity to plus infinity x conjugate omega and e raised power minus j omega t d omega. So these are two terms. इसका conjugate will denote it as x asterisk omega, and e raised power j omega t. In the power it has the imaginary part. You know conjugates, the imaginary parts are have opposite signs, so we put e raised power minus j omega t. So for this we will use this kind of relationship, that is, it will be 1 upon 2 pi minus infinity to plus infinity x conjugate omega e raised power minus j omega t d omega. Fine. And then there will be its own d of t. Then we will rearrange some terms. So we'll take 1 upon 2 pi outside, have the integral minus infinity to plus infinity for omega first, then within brackets I will have minus infinity plus infinity x of t e raised power minus j omega t d of t. Fine. Now this thing here, it is actually x of omega जो यहाँ पे है. Fine. No, sorry, it's x of t, x of omega. This is in like this, x of omega is infinity in this. So same thing I've substituted here. So what I will get is 1 upon 2 pi minus infinity to plus infinity x conjugate omega and x omega d omega. Again, if you have the conjugate, if you have a function at its conjugate, so this will be 1 upon 2 pi minus infinity to plus infinity, and the product of this thing will be the scan of the magnitude. Okay. This is a very important relationship because it relates the total energy content in the time domain to the total energy content in the frequency domain. Like I said, you will learn about the physical significance of this particular property of this particular relation in your communications. Okay. So these are some of the important properties of the Fourier transform. So we have done Fourier series analysis for continuous time domain, and we have done the Fourier transform analysis in time for what you call continuous time signals. Right? There was a lot of symmetry between the two. Next, we will be doing the same analysis for the discrete time case. Again, you will see things will be similar, only that the basic difference will be that instead of x of t, we will have x of n. So there will be some minute changes in the way we represent these signals, but you will see as far as properties are concerned, there will be a lot of symmetry. They will be quite similar to what we did in the continuous time domain. So next videos will take the Fourier analysis for the discrete time case.